Good day. In this video, we will be looking at the application of MATLAB in solving some application problems in differential equations. So we have here the first example. We have the mixing problem. So at the case is, for example, we have a time t is equal to 0. That's the initial condition. So you have a tank containing Q sub O pounds of salt dissolved in 100 gallons of water. Assume that water containing 1/4 pounds of salt per gallon is entering the tank at a rate of R gallons per minute, and that the well-stirred mixture is draining from the tank at the same rate. So set up the initial value problem that describes this flow process. So find the amount of salt QT in the tank at any time, and also find the limiting amount QL. Sorry, that's L. So that is present for a very long time. And if R is equal to 3 and Q sub O is equal to 2QL, find the time T after which the salt level is within 2% of Q sub L. Also, find the flow rate that is required if the value of T is not to exceed 45 minutes. So it actually has many cases in this type of problem. So let's look at these statements or the case one by one. So you have here this image of the tank. So you have an inflow of water at the rate of R gallons per minute and another outflow at R gallons per minute. So basically you have a steady state system. That is your the tank, the vessel itself, the volume of the vessel doesn't change. What changes is the percentage or the amount of salt in the vessel, in the tank. Now you have an initial condition. Initially you have the tank at 100 gallons of water. So even if there's an inflow and outflow, since this is a steady state, you still have 100 gallons of water inside the tank. But the initial condition is you have a value Q sub O, a variable Q sub O as the initial amount of the salt in the tank. And you have here an inflow of 1/4 pounds per gallon and an outflow of let's consider this homogeneously mixed homogeneous mixture. So you have an outflow going down at a rate of the same rate as the inflow, so R gallons per minute. So the easiest way to do this is to write, or aside from drawing the tank for the flow rates, it's also a good idea or a good practice to draw or to write it in a table. So in your table, you have here, I had my table at a time, column time, and then this is just the label column, because you have here the salt and the solutions flowing in. So at time is equal to 0, you have a vessel, the amount of salt inside the vessel is Q sub O, and you have the amount of solution, so that's 100 gallons. So Q sub O pounds in 100 gallons. So when the inflow occurs, so a time at greater than 0, so when we start the clock, so we have the salt and the solution. So let me have this one. So you have a solution flowing at R, small letter R, gallons. So that is gallons, pounds, sorry. R gallons per minute. So R gallons per minute. And going out, that's also R gallons per minute, of a rate of R gallons per minute. And then you have the amount of salt. So for the amount of salt, you have 1/4 pounds per gallon. So, and times the R gallon. So in terms of gallons, so let's say this is in minutes. So R gallons in a minute. So in terms of minutes, how many pounds? So this 1/4 pounds per gallon times. So to get the pounds per minute, you get 1/4 R pounds per minute. Because you have pounds per gallon. So to remove the gallons, so basically basic dimensional analysis. So 1/4 pounds per gallon multiplied by R gallons per minute. So you remove the gallons. So you'll have this one. And then you will have the amount of salt in the vessel. We can say this is Q sub T. This is in terms of pounds per minute. And this is still 100 gallons. Okay, going out. Going out, you still have R gallons per minute. But what's the concentration of the salt? So considering this is a continuous homogeneously mixed solution. So once it comes inside, it's thoroughly mixed. So what the concentration of the salt inside is the same as the concentration that flows out. So this is pounds per gallon. So to get the concentration, you get the amount in pounds per gallon times the gallons. So this is Q R over 100. Okay, so let me change the, okay, so this is the RQ. RQ over 100 pounds per minute. So why is it RQ over 100 pounds per minute? Because you have QT pounds um, at a certain time, Q sub T pounds for 100 gallons. So get the concentration times the amount of the gallons. So to get the pounds per minute, to get the rate where the salt is flowing out in terms of pounds per gallon. So the concentration is Q over 100 multiplied by the volume going out. That's why you get RQ over 100 pounds per minute. And you have now your differential equation. The change in the concentration of salt, so that's Q, over time is basically salt in minus salt out. So what is going in? This is 1/4 R or 4R. Sorry, 4 over, sorry, this is not 4R. This is R over 4 minus QR over 100. Okay, now for the first case, find the amount of salt in the tank at any time t, where this is we get the function q sub t, and find QL as the approaches infinity. So basically, this is this part. So we now have set up the equation and the setup, the equation and the values that we need to have, and we want to find the amount of salt in a tank at any time. So Q of T, and find the limiting amount QL. So when T approaches 100, Q, what is the value? What would be the value of Q as T approaches 100? So Q approaches what value as T approaches 100? So let's look at MATLAB. So I already prepared here a live script for this one. Okay, so another mistake on this one. So this is supposed to be R over 4. Okay. So this is R over 4, QR over 100. So this is basically our equation here. So dq over dt, this is our differential equation, is equal to R over 4 minus QR over 100. So I just put it here. So this is our mixing problem. So this is basically in MATLAB, you have, this is what you call a live script editor. This is different from the command window. This is the command window. So in the previous class, we had the command. I just put it all in the command window. This time, so that I'll be giving this to you so that you can have your notes on this one. So this is a live script. You can have here a combination of text. So this is a text and this is your script. That is a code. This is in terms of a code where MATLAB can run it. Actually, I have run this scenarios before. So let's so how do we but let's go on over it one by one. So how do we first what do we do first? So first we need to analyze the problem, which we already did in this Word file. And then we have our now differential equation based on our analysis of the problem. And then for the MATLAB, we must first identify your variables. Now, MATLAB has a system for the types of variables it has. So it can have doubles and you can have symbols. So when you have doubles, so basically you have a numerical value. So it can be, you can do mathematical calculations on that type of value. But if you have a symbolic variable or symbolic value, that is basically regardless if it's in a say it's a numerical value. If you identify it as a symbol, it identifies as a variable. such that it's a letter or it's a non-numeric variable. So in this scenario, we first identify it as a symbolic variable. So in order to name a symbolic variable, so we have the command sims. So that means it's symbolic. So sims of q as a function of t and sims of r, because we have q and r and of course t as our variables. And then we set up the first differential equation of q and q over t. Now take note, here is the equal sign and there is another equal sign, but this one is an equal sign. So what's the difference? So in MATLAB, similar to other computer programming languages, so you have this we name this variable de1. Basically, it signifies I like to imagine it's a vessel. So I name a variable or a box that is my vessel where I will store my whatever I want to store in that. And in this case, I want to store the differential equation in my variable, in my box, de1. So in order to do that, I name it that the equal sign, the first equal sign, only one equal sign, it delegates that this box, this de1 should contain this differential equation. Now, this equal sign, on the other hand, designates that it has the same value as this equal sign in our equation, in our actual equation. So it's more of a symbolic, in a way, loosely considered symbolic version of an equal sign. So this is basically it's a comparable, or what is that type of character. So this delegates that the dq over dt, that's differential equation of q and t, is equal to our expression here. So this double equal sign has the same function as the equal sign in a differential equation. So we now have this equation. So I will run this section. Actually, MATLAB is running all sections here. So let me have section breaks. Okay. So let me run this section again. So this is a delta t. So actually, let me clear outputs. Okay. So let me change section breaks. So I'm going to delegate section breaks so that we can do this step by step. Oopsies. Okay, section break. And then other section break. Okay, and then for case 2 and case 3. Okay. So we have this first section. So sims. So we define our equation. So this is qt. We name our functions qt and r. So in here, this is a command window, and this is our workspace. Actually, this one is already cluttered. Let me clear the workspace. Okay. So initially, if you are starting up, you have, when you first run this section, so you have this output, and from the blank one, you have now in your workspace several variables. So you have the q here, q and t. So this is q is now a symbolic function of t, which is a symbolic variable t, and then another symbolic variable r. And then we have de1, which is a symbolic function also. So when I say one by one, so it's just one by one matrix. So it's a single element in this box or in this container de1. So here is our differential equation. So dq dt of the function qt is equal to r over 4 minus r q as a function of t over 100. So this is our equation. Now let's set up our initial condition. Now in our problem, qo is a variable. So we don't have an exact name for qo. So therefore we just say a symbolic variable qo, and also define the initial condition q sub o must be equal to qo. So whereas q this means that Q, where the value of Q when T is equal to 0 is equal to Q sub O. Notice the double equal sign and a single equal sign here. That means, just like in this DE1, icon is the container for this um, initial value equation. And so we can run this section. So we now have the initial condition, Q sub O is equal to QO. So if you look at our workspace, we now have a new variable, Q sub O, and a new symbolic function. Actually, it's a symbol, so icon, that is um, the icon here. Okay, so moving on. Now we get the general solution for this equation. So I put it as a G-sol, as a function of T. So we solve, so this solve is one of the, not the only, but this is one of the solvers for differential equations in MATLAB. So we also have ODE 45. Actually, there are different solvers. The issue here is because MATLAB, when it solves differential equations, the way it solves is a bit different from how we actually solve it using pen and paper. Some MATLAB tend to use approximations to solve your differential equation. So anyway, in this the solve function, you input your differential equation and the initial condition. So actually, if you look at MATLAB, you will see here equation 1, equation 2, condition, and options. So here is the syntax for the desolve, and it's actually quite helpful when you type. So I'll run this section. So I got this solution, the solution of QT. So if you look at our workspace, we now have your GSOL, a symbolic function. So take note, this is also a symbolic function. You cannot run an equation, or it cannot solve an equation or a numerical value here. So you have E minus RT 100 is equal to Q sub O minus 25 plus 25. So that is our general equation. So that's the general solution. However, we look at the first case. So what's the amount of the salt in the tank at any time T, or Q sub T? So basically, this is our Q sub T. So G-sol is the solution of your differential equation given these initial conditions. And this is G-sol of T is actually Q of T. And this is the equation that signifies the amount of the salt in the tank at any time T. Now, what if our T approaches infinity? After a very long time, what happens to our T? So provided, because we have an R and a Q sub O symbol or a function, in order to solve this one over at infinite time, so we assume the equation tells us that find the limiting amount provided that R is 3 and QO is 2, twice the consistent or the stable value of the salt concentration. So we have Q sub O. Sorry. So first I assign values here. Not that. Okay, so this is not, sorry. I think this is Q, not QO. So this is QO. I forget the QO. The QO is 2QL. Okay. Q sub O is 2QL. So since we don't have an initial amount of Q, I just put up an arbitrary value of 0. But I put up R is equal to 3 because anyway, this was already given in the equation. So I just assigned this value for this one. Okay, now since we have this equation, this is a bit of a I do admit there are shortcuts for this one, because now the problem here is our Q G sol of T, which is the solution. It describes the amount of Q over a time T. This is a symbolic function. So you must change the symbolic function to a non-symbolic function. And my way to do that, there are other ways. If you look at MATLAB helps, there are other ways to convert it. But I just go to the brute force method, the simplest one, which is to just copy this equation and provide for the values of R, Q, O, and T. So in here, I named it because our first R is a symbolic function. So let me change this value now into a different R. So I put it as R so that this will be different from, or let's just say R now. Okay. So that this number would be different from the symbolic value of R. And then Q sub O is equal to 0. Let's say this is QO, let's say this is number, so that this is a numerical value. And then this is our T, numerical value T now. So this is, I did this on the fly right now in order to distinguish the symbolic T, Q, O, R, and Q from our equation. So our Q is, because I just copying the G solution, so this is, I signed it because this G sol is actually Q of T. So this is the numeric value of Q. Q num is equal to, I just write this, XP minus R times T over 100 times Q O minus 25 plus 25. And so this is our Q now. And I want to plot this one. So let me first rename this one so that I would not get an error. So this is R num, this is T num, and this is QO num. So that's numerical. Okay. And then plot Q num. So let me run this section. Okay, so we now have this equation. So it actually plateaus near 25. So let's see, since we want it as T approaches infinity, let's have QO extend, let's extend QO. So I want Q num O to have multiple values. So Q num O from the values 5 to 50. So this is, I assigned here a value 0, 5, 50. So that means from 0 to 50 at the interval of 5. So when you write it, you have a semicolon. So the middle one is the interval, and then you have this last digit number. Now, if you just simply, if the interval is 1, you can omit this one and just write 0 to 150. So I want it to go forward 150 minutes. So this is again T num. Okay, and then Q num, let me change. R num, this is T num, QO num. Okay, so I'll be changing now. I'm still using the same values because I just want to change these values. Okay, and then run it. Now this is a for loop, if you notice. So this is a for loop. So the for loop means that for every value of Q num going from 0 to 50, so this is a number that has a set value. You get a number of T from 0 to 150, and then you calculate Q num and you plot it. And then you have hold on, which means that it won't erase the initial plot when it loops back to another plot. So it will run, or it will draw the plot in a single figure. So let's run this section. Okay, it's not. Okay, Ionia. Let's see. R num of T num from 0 to 100. So let's see. Q num. This is a double value. Zero to 50. 25. Why does it like that? Okay, so I found the issue. I had a different value. This is Q O num and the Q num. So the previous one, you have a different, it's a syntax error on my part on this name of the variable. So anyway, so let's run for Q O num 0 to 5 to 50. and this is QO num. So that means for every run of the loop, this QO num is increasing by a factor of 5 from 0 to 50. So I extended from initially we have up to 100 minutes. So this is up to 100. I extended it to 150 so that we can see more if it's converging to a certain value. So this one, it looks like it's about to appear to 25. So let's run it. Okay, so now here is your plot. So here are the values for each loop. So at initial value QO at 0, at 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. And as you can see, no matter the value um, of our initial salt concentration, it still converges to a certain value, and that is 25. So from where this plot converges, our Q sub L, so when t approaches infinity, even if we extend the time, we will go near and near until we get 25. So this is the answer to case 1. So you have this value. So here is one way to plot. This is more of a brute force approach for plotting, but anyway, it works. Whatever works for you, basically the output is what is really important here. If you can apply, um, there is a subs function where it substitutes a certain numerical value for a symbolic function. And you can also evaluate. So there's an eval and a subs functions, but I'm still figuring it out. So I'm just using this brute force technique for now. Anyway, case 2. So for case 2, so case 2 tells us that for r is equal to 3, so as case 2, r is equal to 3 and q sub o is q2 ql. So since our ql is 25, what is 2 ql is 50. So it's the time t after which the salt level is within 2% of ql. Now here is where I ran into some difficulties initially because I had misunderstood this within 2% of QL. So it's a common mistake where you would say that, oh, basically our Q should be 2% of QL. But 2% of QL or 2% of 25 is a very small value. So it's around this value. So if the initial condition of our QL is 50, if our QL is 25 and our 2QL, that's our initial salt concentration, is 50, it would never go down to 2% QL, which is 0.02 times 25. So this is what it means is that your value of QL must be plus minus 2%. So it's either 98% or 1.02%. So since we are coming from a higher salt concentration than the equilibrium value, so let's approach it where it is 1.02%. So in this case, I have here another symbolic function sims of 3. So I have this value r num, which is a 3. Now, you have here QO, numerical value. So I'm just overwriting again the numerical values from here. But anyway, where am I? Case 2. Okay, so Q num is 2 times 25. So this is because QL is 25. So I did not input an additional variable QL. So I just put it that to QL is 50 and put it as our QO num. So initial condition is at 50. So I have our Q. So this is the numerical actually have this as Q. So I had it as Q because this is a symbolic function. So when you have a symbolic variable here, all of this becomes symbolic. So we have this Q. Q is equal to this equation, which is our equation from before. So let me just update the values. R num and QO num. Okay, R num and QO num is equal to 1.02 times 25. This is because we are coming from a higher value than the equilibrium value of Q. And within within 2% is means plus minus 2%. So it's either 102% or it is 98%. So since coming from a higher one, get the upper limit, that's 102% or 1.02 times 25. So that is the equivalent. That's our value of Q. And then we have an additional, if you have a D solve for solving differential equation, I have T solve. So this is for solving the linear equation, because this is just a simple linear equation. Actually, not exactly linear, but a simple equation. And since this becomes your capital T becomes, even if we solve it, we have this value of it will become a symbolic function because we have a symbolic value. So I will be introducing double. So the double function or the double command converts as a a symbolic value to a numerical value. So the t, which is a symbolic because we solved it, but one of the variables is a symbolic, so all of them become symbolic. So it is also a symbolic. We want to convert it to a numerical, so I had it double t. So let's me run this section. Okay, and we have now our value. So if we substitute or we find t in our equation, this is the value of our t. And if we calculated the actual value, this is 130.408. So that's the amount of time. 130 minutes is the amount of time it would take for our for the solution or the vessel to go within 2% of our QL. So around 2% here. So actually, if we look at our graph, this is 120, 130. So within 2% around this part or this period. Okay, so the last one. So what now becomes, we want it faster. We want it to change faster. So if our flow rate, what now becomes the flow rate if the T, if we don't want it to become 130 minutes, we want it to become 45 minutes. So what should be the flow rate now? So again, I now have the same approach as this one, but I change from T to R. And I have T as a numerical function now as 45. So QO is 225. QNum, same case. This is R. This becomes TNum. So I'll just put it as a numerical. So TNum is 45. QO num. Okay. Is equal to. And then R solve, the same approach. And the rate should be 8.63 gallons per minute. So anyway, that's how you do apply MATLAB in solving for some differential equations. Okay, so in the next videos, we will be looking at other examples.